Pero no puedo. preguntar? ¿Qué diferencia es estar allá? Que va a ir de acá.
Así es que siempre lo vamos para acá.
Y ahorita se va el otro. Ah, sí. Pero pregunta a ver si no. Pregúntale qué pide. Es una vez. Aparte se supone que la regla es como para que todos. No. ¿No te ayuda? Ah, pero está en la cámara. ¿Por qué está bien igual? ¿En serio? No manches, ¿en serio? Pero también creo que fue así, nada más de dos.
Me compramos en el que lo libre 50.
Es de videojuego, ¿no?
Yo quiero cargarlo de la mochila, venga a cargar.
Y siempre perdía mi celular así.
Más no es causal, o sea, no es lente, pero tampoco no es lente. Tú eres el experto en la guerra, ¿no? O sea, no hay causa, ¿no? Usa lente, así que ya la coloración. Y yo al final sí que ¿Es un nuevo vídeo? Sigo decepcionado, voy a poder olvidar esto. de lana, ¿sabes? Tiene rombos de... ¿Cuánto tiempo? 195 menos 200, 145, ¿no? Pues tiene un...
Está bien. Ah, ya son ocupados. Son ocupados.
Ah, pues sí. Por ejemplo, es como estar en el gol aquí, güey, y hacerte. Y el speech de. ¿Cómo se llama? Si nos contara eso, güey, así como. Que ya estoy incluido. Puede ser que todo lo haya ahí. Pues ahorita ya estoy pensando en el día. No sé qué pedo. Y bueno, sí, la siguiente. No sé qué pasa, ¿no?
Son las notas que cuando los había una que habla bien.
Ay, no, es que le hablo bien, güey. Es que me da que la mamada. Es un compa con el que juego, güey. Y me dijo, decía, no, dile que me ayude. No voy a decir porque es clase, güey. Se cree ética y todo eso. Y ya como que me dice, vale, o sea, de por sí ya los ayudó. Pues me dijo, si me dijo, pues me puso dudas. Y recordaste el equipo, ¿no? De la vida.
Sí, luego mandó un mensaje y decía, oye, no recuerdo eso.
Ah, bueno, sí, no me puse.
Es como que, ¿qué quieres que haga? Digo, tú, si cumplieron esto, ajá, no sabía eso, ya no puedo.
Qué pendejo. Y esa onda de pelos. Niñera. Es que él es de Chiapas, pero por eso que su persona estuvo como que todas las personas eran los. Sí, digo, no sé si voy a hacer para algo que vale culo, ¿no? sé porque de verdad me gusta.
Eso de bronce.
No, yo pero nunca te lo pongo aquí. Nada, a lo mejor por según yo es una combinación de aquí ahí. Pero cuando lo hizo, mira, ya luego todo cambió cuando hizo la balada.
Sé lo que tengo que hacer.
No, pues sí, porque pero te supongo mucho mejor. Que es de 4, ¿no? 394. Que fue muy bien. Es materia, güey. Qué bueno.
In human genetics, and after the first 10 years of what we call the GWAS era, the genetics community was able to identify more than 20,000 associated variants, and the largest cohort reported by 2017 had more than 1 million individuals. So now, what is genetic risk prediction? And I'm going to describe the methods that we use to build these methods. So, of course, the goal is to use genetic data to predict a quantitative trait. It can achieve high substantial accuracy when we have very large training sample sizes. And polygenic prediction that uses most of the large amount of common variation and not restricted only to the genome-wide significant variants tend to outperform the other scores, the ones that only use significant variants. And also, the genetic heritability imposes an upper bound over the maximum prediction accuracy that a model can attain. Methods to perform polygenic risk prediction can be divided into two categories. Methods that use summary statistics only, which usually are publicly available, and methods that use and analyze individual-level raw genotypes and phenotypes. So, in principle, methods that analyze individual-level raw genotypes and phenotypes can attain higher prediction accuracy by fitting all the genotypes at the same time. However, we need very large training sample sizes to do this. And this is a limitation because of sharing data policies and having access to these large databases is quite restrictive for most of the research community. So we have an special interest of methods that analyze summary statistics only, and these are the ones that I'm going to talk about. The genetics community has pushed a lot for open sharing of GWAS summary statistics, and this is a survey based, of course, there's a lot of information, but I just wanted to be able to portray the large amount of publicly available summary statistics that are out there. Many of these data sets, the GWAS summary statistics were computed using cohorts of more than 250,000 individuals, so they tend to be very powerful. What is polygenic risk prediction? The goal, of course, is to build the best predictive model, and this problem reduces to a variable selection problem as well as a regularization problem. And the typical model that we assume is the additive genetic effects model in genetics, which is commonly used. The first method to incorporate and compute a polygenic risk score it was a very heuristic approach that tried to balance the signal-to-noise ratio by optimizing over the p-value threshold of the genome-wide associated variants. And it dealt with the correlated nature of the genome by applying LD clumping. This is for every 2 correlated variants, we keep the one that is the most significant. Another way to correct and account for LD is through a multivariate model and directly compute the correlation between SNPs. This is applied in a method called LD-PRED, which is a Bayesian approach that imposes a prior over the genetic architecture of the disease and accounts the correlation between SNPs. And as you can see here, the prior is the same for each variant. So we are assuming that each genetic variant contributes the same to the total heritability of the disease. We extended this model to incorporate functional information. So we use a method called stratified LD score regression that allows us to estimate the individual per SNP heritability of each SNP or each genetic variant. This model allows us to use also publicly available functional information and incorporates up to 56 functional categories that include coding, exon, histone marks, conserved regions, and also continuous related annotations, which can include like allele age, recombination rate, etc. And by using this method, we are now able to have a unique prior for each variant. So with this, now this allows for different shrinkage of the posterior mean causal effect sizes depending on their functional enrichment. So it's depending on which region each variant lies, how important it is. So I wanted to show you a brief example of the application of all these methods. And a very common trait that we use in genetics as a proof of point is to predict height. This is because it's highly polygenic and it's highly heritable. So I'm presenting here results that where we applied these methods. We use as training 100,000 white British individuals from the UK Biobank, and we predicted over 25K Irish and other white Europeans. So basically the take-home message is that including functional information over non-functional informed methods, we attain a higher prediction accuracy and a statistically significant improvement. And methods that directly model LD prove to be better than methods that heuristically account for LD. And we were able to predict up to 41% of height, raising the prospect of predicting this disease risk, of the clinical utility of predicting disease risk. So I want to show you some other clinical applications. The first one is a study done in the UK. So the researchers built a polygenic score using only 77 variants. And they identify, and this study was associated to breast cancer. And they identified that, for example, individuals that were at the upper tail of the distribution could benefit from earlier screening for breast cancer compared to the average recommendation, which is usually at 47. So for individuals that were in the upper tail of the distribution, the recommendation should be actually to start screenings earlier. Another very important study that came out last year and that caught the attention of many of the genetics community and in the general public was a polygenic risk score study that predicted coronary artery disease. They use actually LD-PRED, the method that I just described, and they implemented and they trained the model using 6 million variants, and they constructed a polygenic score. they found out that in the upper tail, they could identify a subgroup of people that were at high risk, with an odds ratio larger than 3 for CAD compared to the rest of the distribution. This effect size actually compares very similar to the effect size of a monogenic variant associated to CAD that only affects 0.4% of the population. In the case of this monogenic variant, people that have this variant, they can, if they receive interventions that lower their cholesterol, I think, they can decrease their risk of CAD. So basically what this is telling us is that the individuals in the upper tail have like this combination of risk alleles that in bulk act similar as if they were monogenic. But the story is not over. Actually, polygenic risk prediction in non-Europeans is still a challenge. It is not a mystery that genomics is failing on diversity. Here I'm showing the current state of GWAS studies across the world, and basically most of the studies have been done in the US and the United Kingdom, and despite the fact that these two countries are very diverse, they actually recruit mostly white European ancestry individuals. So this translates into a reduction of prediction accuracy when applied the methods that are trained in Europeans into other populations. The main reason for this is because of differential tagging, basically because of the different patterns of LD that I mentioned before. Different ancestries have different genetic LD patterns, and this translates when using only European training data and predicting in other populations, we can reduce the prediction accuracy up to half from what it would be expected if we were going to predict in another European population. So we proposed a solution for this. Let's think that the real scenario is that we will always have more European training. That's a fact. But how can we leverage having information from European and the advantages that large training data sample sizes give us, and also having a training data set that is in a medium or small sample size, but that we have same LD patterns. So we proposed to find an optimal combination of these two training data. And for example, it's validated through tenfold cross-validation. And for example, in an application that we did to predict type 2 diabetes in a Mexican cohort, we identified that our method outperforms single ancestry approaches, despite the fact that we had 5 times more training data in the European training than in the Latino training. And the simplest way to combine, the most natural way to think about how to combine summary statistics will be a standard meta-analysis, and we also outperformed a standard meta-analysis. So, in summary, polygenic disease risk prediction is a prognostic test, and its value can help achieve prevention of certain conditions. We can achieve a high prediction and clinically meaningful prediction accuracies when having large training databases. But it's still a challenge, especially when we're talking about predicting disease in non-white European populations. So, thank you. I want to thank my advisor, PhD advisor, Alkes Price, and all the people in the slide.
Thank you very much. So, thank you. So I remember you that the discussion after the 4 presentations we will have, of course, the discussion of the panelists, and then open discussion with everyone. Okay, so let me introduce you now, Dr. Humberto Sosa Azuela, who received his bachelor's degree in communications and electronics from the University of Guadalajara in 1980. He obtained his master's degree in electrical engineering from Simvestav in 1987, and his PhD in informatics from the Institut National Polytechnique de Grenoble in France in 1982. So he's currently a full-time professor at the Robotics and Mechanics Laboratory of the Center for Computing Research of the National Polytechnic Institute from Mexico since 1996. He has authored and co-authored 3 textbooks and more than 450 journal and conference publications. He has 8 patents and is a senior member of the IEEE. His areas of interest are in artificial intelligence and machine learning, in particular in artificial neural networks, learning algorithms, and their applications. So let's welcome Humberto. El control.
Okay, first of all, I would like to thank the organizers of this RIIAA for the invitation to participate in this event. So, I would like to know how it works, this. Okay, so I will talk in this occasion and what we are doing in our institute in artificial intelligence and machine learning. Okay. We can say that today is a time of artificial intelligence and machine learning. I don't know what's that. Okay, it's not for me. Okay. Oh, something. Okay, so the question is why? First, because we have access to cheaper computing power, we know that. We have much better AI and ML algorithms. And third, because we have much and better data for AI and ML processes. So that's my first. Okay, so artificial intelligence, just to remember. In the one hand is the science and engineering of machines that act intelligently. And on the other hand, ML is a subfield of computer science and a branch of AI whose goal is to develop techniques that allow machines to learn. So taking this into account, I'm very sorry about this. Okay, today is a time of artificial intelligence because both of them are being used in many applications. Let me give you some examples that I found in internet. For example, to deliver groceries, okay, goods, your ice cream, your dinner, maybe pizza. Those are real applications, we know. To help people in a hospital, to help people working, to help people to take care of children at hospital, okay? To help people with this sickness, to make predictions 5 years before, okay? To find vulnerabilities in nets and then patch them in software. To detect fake news and to produce fake news, okay? But one more thing. This is the first book ever published by artificial intelligence. That's an experiment made by Goethe Universität and Springfield Verlag. So I invite you to buy the book or to read it, and you will find that it's correct. It's very nice. Okay, more. Okay, to help cars to park. Okay, this is more challenging. To avoid pedestrian fatalities. To turn at high speeds. And this is a very nice project that I found in China. The common bicycle. More things. To play, to invent sports for men. What else? Okay. Try to this with these concepts. Okay? To do some jobs in the supermarkets, to make gourmet burgers every 30 seconds, and more. Okay? To planify, it's not very easy, eh? Okay? To deliver, to plan your trip, to predict even volcanic eruptions with accuracy. These are the next generation. This is the next generation of robots that are going to go to Mars. Okay, using AI to make better AI. And I end with this. You know, our 3 colleagues obtained the most prestigious award. So for me, this is a conclusion that artificial intelligence now is to be here. Okay? Now, I go, what we are doing in the National Polytechnic Institute, so I will face in 3 axes. Education, you know, it's very important. Generation of knowledge and application of knowledge to solve real problems. So, concerning education, we know that in Mexico we need people, specialized people in artificial intelligence, machine learning, data science. So next year we are opening 2 careers. Sorry about this. Artificial intelligence engineer, data science engineer. And then we are working in 3 postgraduate programs, 2 masters and 1 PhD each. So we are working on how we organize the work by establishing research networks. So we are establishing a research network in artificial intelligence in data science. For the moment, it gathers 55 permanent people and about 600 students, not too many. But you see a lot of power there. Okay, now, in particular, where we are doing, just I will give you some lines. In our research center, we are working in artificial neural networks, brain programming, service robotics and social robotics, natural language processing. We have some colleagues here that represent this area, and in pattern recognition, image analysis, and computer vision. So I will give you some examples, specific examples. Okay, for example, combining morphological perceptrons with dendritic processing and multilayer perceptrons for deriving new hybrid architecture. So this is a PhD. Using gradient descent techniques to tune the weights of so-called artificial neural networks with hyperelliptical dendritic processing. Maybe some of these words are some strange for you. Using polytype theory for dendritic processing and this kind of networks. We are also using spiking neural networks to be applied in EEG signal processing. What else? We are working in the design and the implementation of a real neuromorphic computer for spatial temporal analysis. We are working also using deep learning techniques, for example, for autonomous rover navigation in a known and non-heterogeneous environments. We are also using this technique for irregularity terrain detection for autonomous navigation. Brain programming, for example, applied to cancer diagnosis from images. And now we go to the technological part, which I think is very important. So we are working in a prototype of a bicycle. It's not finished, of course. We have 2 patents under review and 3 more under preparation that are concerned with techniques and, you know, devices for this kind of technology. Second, we are working in the design of intelligent apparatus for medical diagnosis, for example, stethoscope, electrocardiogram, and electroencephalogram. What else? This is a very important problem for those that know which is SNE. We know that in our national system of researchers, we have more than 2,500 case files that have to be evaluated every year. And the number is rising up, okay, every year. And the whole evaluations is made at hand. So we propose to CONACYT to develop a system that automatically evaluates all the cases. And we are now working and we are now preparing the technical economical proposal. And to finish my talk, you know that automatic paper also for journal is a very complex problem. Every year, millions of papers are received by journals to be reviewed. More journal papers than the number of reviewers. It's an exponential data problem. The evaluation process is literally manually done. So the idea is to design and put into operation a system that automatize most of the evaluation process. We are aware that this is a very difficult problem, so we are preparing a proposal for a journal, and we hope to have some results in about 2 years. Thank you very much.
Thank you, Humberto. So let's gonna start with Antonio Terán. So Antonio Terán is a doctoral candidate at MIT Department of Aeronautics and Astronautics, of course. He has been a visiting researcher at NASA's Jet Propulsion Laboratory and Ames Research Center, and more recently at Google's self-driving car enterprise, Waymo. So his interests include space exploration, mobile robotics, and probabilistic inference. Again, let's gonna welcome Antonio.
Thank you. Oh, perfect. Clicker works, so it's good to go. All right, hi everybody. My name is Antonio. I'm still a student at MIT's Aeronautics and Astronautics department, and I'll talk about a bit about an application of artificial intelligence tools, or tools that are typically used within the AI field, that were ported to the robotics field in order to leverage all of these powerful algorithms that they support, and for us to tackle more complex missions. So just as a brief outline, I'll start with a tiny bit of the motivation about why is it important for robots to localize and map, and then I'll follow by showing you what the traditional approaches are, what the tools and algorithms that were normally used in order to tackle these problems, and what their drawbacks and pitfalls are. And then how is it that AI research allows us to learn via graphical models and to tackle these very complicated tasks. So to start with, a fundamental question in robotics, and probably also in life, is where am I and what's around me? So, for example, mobile robotics need to be solving this all the time. In order for them to not collide with obstacles around, they need to map. But in order for them to map, they need to know where they are so that they can start building the environment around them. And a more concise application of this would be self-driving cars, for example. Whenever you're trying to drive around, you need not only take into account yourself, but you need to take into account the 5 million irresponsible kids that are walking around, and you need to make sure not to collide with any of them. And what I specifically study is space robotics, and similarly spacecraft, like satellites. In order to carry out all of their missions, they also need to address this as well. They need to know where they are, what's around them, in order for us to make use of the data that they acquire. For example, the Hubble Space Telescope, whenever it's observing something, then we need to know exactly where is it pointing, what its orientation was, where its position around the Earth is, in order for us to know, oh, it's looking at this star, or it's looking at this other star. Similarly, like Landsat 8, it's an observation satellite. It allows us to do Earth observation. And if we didn't know precisely where it was, once we take a picture, it's hard for us to stitch them together or to make sense of all of this data that it's collecting. So in order to do this, we need to tackle the localization problem first, right? And to localize means to estimate the values of the system's current state vector. And for a very simple robot system, the state vector looks like this. You have a position component and an orientation component. And in order to estimate these values, we do something that's called filtering. And filtering is just basically using our previous estimate of the state vector, so a state vector at time t-1, and then the current sensor information that we're observing, be it images, LiDAR, odometry measurements, whatever IMUs, in order to compute an estimate of the current state vector. Right? So this is basically the problem that we're trying to solve. And I would dare say that, I'll stand up. I would dare say that probably the king of filtering algorithms is the Kalman filter. So the Kalman filter is an algorithm that allows us to optimally estimate in 2 steps like data prediction tasks in Gaussian linear models. The way it works, you start with some sort of prior on your state, some means of your state and some covariance of that. You perform some time propagation using some motion model, and then you perform a measurement update. Once you get that measurement information at that time step, you fuse it with your motion model using your observation model, and you obtain a posterior estimate. You do this again, motion model to time propagate, and then measurement update using your information. And as you can see, the cost per step of such an algorithm is mostly dominated by the size of the covariance matrix, since you need to be doing matrix conversions, matrix multiplications, etc. So for really small state vectors, for example, a simple robot in which you only have position and orientation, this approach is super efficient, super effective, super nice, and that's why we have spacecraft operating, Hubble, and all that. But in the future, as mission starts to become much more complicated, and as we start incorporating more agents into all of our endeavors, for example, the typical new space mission that we want to carry out is in-space robotic assembly, in which you send out a plethora of spacecraft, they deploy something on orbit, and then you have a couple of robots that go around, grab the pieces, need to interact with all of them, need to predict how they'll spin in order to start building space stations before humans get there. Or if you want to do on-orbit servicing, you have a defunct satellite that you want to give new solar panels or clean the solar panels. Then you have this complicated dynamics and interactions between multiple agents. Or orbital debris removal, there's a lot of garbage in space that we need to collect. And these are very complex multi-agent proximity operations missions. So for these missions, our state vector is no longer very simple. So our state vector usually looks a tad more complicated. For example, we have m number of satellites. We need not only care about ourselves, but about the agents around us, as well as some sort of map representation, some sort of landmarks that we need to track. So you can see that this is really big. So a very simple example in which we have a robot it's on red, and then it's exploring a world of landmarks, which are blue. At first, we need to just carry a very tiny correlation metrics, but as we start exploring around, we see that this starts to grow once we incorporate more landmarks, and if we keep exploring, it keeps growing. So after a certain amount of complexity, this algorithm fails, and we can no longer tackle very complex missions. Hence, we look to the AI field for some insights to see what we can leverage in order to make this tractable. So how can we do better? Exactly what I said. So we can formulate all of this estimation problem as an optimization. We all know that optimization is the workhorse of AI, machine learning, and everything in the universe. And we use probabilistic inference techniques in order to use graphical models for this. And what we end up having is a SLAM problem. And this is specifically my area of research. What does SLAM mean? SLAM means simultaneous localization and mapping. And it's a problem whose objective is to estimate a robot trajectory, its neighboring agents, as well as the environment around you. And SLAM usually involves 4 main ingredients. So ingredient number 1, it's a robot poses, so position and orientation at each time step that we want to explore. Ingredient number 2 would be the landmarks or the map around us. In this trivial example in which we have a car, with the trees would be our map that we're trying to estimate. Number 3 is the control inputs. So the agents that we're actually controlling, we need to exert, for example, steering angle and speed that we want to control this vehicle. So we take that into account. And last but not least, we have all the measurements that we collect around about the environment. In this case, for example, we can collect range and bearing from the car to the tree. So we use these 4 ingredients, and what we actually want to obtain is, or what we actually obtain is this optimization problem in which we have a joint probability distribution described by these 4 main ingredients, and what we're actually interested in finding out is the best estimate for all of our robot poses and the best estimate for all of our landmarks. So localizing and mapping. And how do we solve this? Well, one cool way in which to solve this is encoding a SLAM problem into what's called a factor graph. And Joshua Vengio already talked about what a factor graph is, and it's a nifty way in which one can graphically represent joint probability distributions. And in this case, for each node of interest, for example, we're interested in car poses and landmarks. We had a variable, so a node. We're interested in the robot poses and landmarks. And then in between each of these variables that we're interested in, we have some sort of constraint. And this constraint comes in forms of measurements. For example, we have a measurement in between this car and this tree, which is sort of like a range and bearing. Between the two car poses, we have some sort of odometry constraint that's provided by our IMUs, for instance. So once we do this, we are able to leverage very powerful inference algorithms that are used all the time in the AI world. For example, we can encode this joint probability distribution graphically, which we can then translate into math by using a nonlinear squares method in which we're assuming some sort of Gaussian errors between our variables, and so we weight them through here. And after explaining this, we can just use graph-based algorithms for inference. For example, a very common and general graph-based algorithm would be belief propagation, and some specific examples of that would be sum product algorithm and maxsum, which would allow us to compute all of these estimates that we want. And an algorithm that's specific for navigation would be incremental smoothing and mapping, in which we incrementally add all the sensory information that we acquire into our factor graph. We append another factor, we append another node, re-estimate, and that's how we can explore the world. And how does space enter into this? Well, my research deals with testing algorithms in space. So testing navigation, estimation, and mapping algorithms in space. And what my lab at MIT has is this 6 degrees of freedom, long duration microgravity testbed that's actually floating on board the International Space Station. This testbed is called Spheres, and Spheres, you can see an example of it here. It's like a spherical robot that has 12 thrusters, so full actuation. We have 3 of them on board the International Space Station, and they float inside a volume that's 2 meters cubed. And in order to do the mapping, I use a stereoscopic camera attachment called Vertigo, in which then we can develop vision-based relative navigation algorithms. So in this case, I'll just show a few examples. This is more or less how the pipeline works. We develop some ground tests that we test at our lab at MIT. Then we deploy the algorithms into the space station, and then we have help from astronauts, which operate the satellites and run the tests. So they click enter in the computer. And so our satellites float around, gather data, and then they allow us to test like real estimation algorithms in a fully microgravity real environment. For example, we have an example of collaborative inspection between 2 sphere satellites. And here we have an unknown tumbling target that we want to identify. For example, let's say that this is a defunct satellite that we want to stop and bring down in order to remove debris. And this is a very nice example that one of my colleagues obtained, in which you're doing your visual odometry perception, you're doing your centroid tracking, you're building the map of the object that you're doing, and you're estimating all of the physical characteristics online. So it's pretty neat. And just to conclude quickly, it's really nice that we're able to formulate navigation problems using the language of factor graph, and we're able then to leverage algorithms that are traditionally used within the AI community, like sum product algorithm, belief propagation, factor graphs, micro-random chains, all that in order to leverage them and solve very practical engineering applications. And that's it for me. Thank you.
Great. Thank you. So, our final panelist, last but not least, of course, is Carlos Coello. He obtained his PhD degree in science, in computer science, from Tulane University in 1996. Since 2001, he's researcher at Departamento de Computación at Simvestav, APN. He has more than 480 publications, reporting more than 45,700 sites on Scholar Google, with an H index of 83. And among some other distinctions, He received the National Award in Science and Physical-Mathematics Science in Natural and Science in 2012, and the World Academy of Science Award in Engineering Science in 2016. So let's welcome Carlos Coelho.
Thanks a lot for the invitation and for the introduction. So since I don't have much time, I'm going to talk about an area in which I have been working for the last 25 years, very quickly, but I hope you find this area useful in case you're not familiar with it. Multi-objective optimization is a branch of operations research in which we deal with some sort of ill-defined mathematical problems. We have problems with two or more objectives, but the issue here is that these objectives are normally in conflict with each other. So for example, I want to optimize the design of a bridge. And normally, the two main issues when designing a bridge is to minimize the cost and maximize safety. These two objectives are in a contradiction because normally if I want to increase safety, I have to put more money because I need to reinforce the structure. So this is the sort of problems we're interested in this area. So normally, Normally, the first issue in multi-objective optimization when you get to this field is the notion of optimality. In global optimization, is very obvious what the notion is, but in multi-objective is not so obvious. And actually, there is more than one definition of optimality. The one that most people use was originally proposed by Francis Isidro Edgeworth. He was a professor at Oxford University in a book published in 1881, Mathematical Psychics. And it's a notion that refers to finding the best possible trade-offs among the objectives. This notion was generalized by the Italian economist Vilfredo Pareto in 1896 in a book published in French, Cours d'économie, in which he used the term of illimity to refer to this notion. And today is normally called Pareto optimality. They forgot about Edgeworth. And this is the definition. If we assume we are minimizing all the objectives, and this is something we can always do. If we have, that if we have a vector of decision variables that is feasible, that means the solution satisfies all the constraints, then it's Pareto optimal if we don't have any other feasible solution that fulfills these two conditions, that is less equal in every objective and strictly less in at least one. So this basically says that I want to find solutions in which it's no longer possible to improve one objective without worsening another one. Obviously, if there is a conflict among the objectives, this is going to give me not a single solution, but a set of solutions. This set is called the Pareto optimal set. The vectors contained in that set are said to be non-dominated, and the image of this set, the objective function values, are called the Pareto front. Of course, in evolutionary computation, we didn't start the area. The area had started in the 70s in operations research. And there are a number of methods in the literature to deal with multi-objective optimization problems of all sorts. In here, I'm referring mostly to nonlinear multi-objective, but there is also, of course, linear and combinatorial multi-objective optimization. But these methods, at least the ones for nonlinear multi-objective optimization, have several limitations. The main ones have to do with the fact that they are very sensitive to the shape and the continuity of the Pareto front. If the Pareto front is disconnected, for example, many of these methods don't work. Also, most of them require specific domain information, like the derivatives, which are not always available. So the use of evolutionary algorithms in this field comes from the very origins of the area. As you probably already know, evolutionary algorithms are inspired on natural selection. They are stochastic search techniques that are based on the use of random numbers, and we try to imitate somehow, to mimic the process of selecting solutions based on fitness. So any stochastic algorithm that has a fitness-based selection mechanism can be, strictly speaking, be considered an evolutionary algorithm, although selection is not the only component. We also have operators, normally crossover and mutation, and also there are a few other components that are normally added to traditional evolutionary algorithms. But The main evolutionary algorithms are genetic algorithms. These are perhaps the most famous. Then evolution strategies that were proposed in Germany. And evolutionary programming was also proposed in the US, same as genetic algorithms, but they are not as popular. Evolutionary programming is actually the least popular of the three. And we also have genetic programming, which is a variation of the genetic algorithm. It's not considered a different evolutionary algorithm. And in recent times, we have other algorithms like differential evolution, particle swarm, which some people consider an evolutionary algorithm, others don't, because it doesn't have a fitness-based selection mechanism. So evolutionary algorithms seem very suitable for multi-objective optimization because besides being a robust optimization engine, they operate on a set of solutions. So if we can properly manipulate the selection mechanism, it should be possible to generate several elements of the Pareto optimal set in a single run of the algorithm. This is not possible with most mathematical programming techniques, which operate with a single solution at a time. Also, because of their stochastic nature, evolutionary algorithms are less sensitive to the shape and continuity of the Pareto frame. The main disadvantage of evolutionary algorithms has to do with computational efficiency. They normally require a significant number of objective function evaluations because they are stochastic and we need to sample the population. So these costs may be prohibitive in some applications. In the old days, and part of this is my time when I was a PhD student, in the old days, that goes from 1984 up to early 90s, people used the non-known algorithms. They were non-elitist and non-Pareto based, which means they were very naive approaches. I'm not going to get into the details on how they work. But basically, most of these approaches consider a single objective at a time, either adding all the objectives into a single value or giving preference to a particular objective in a moment of time to do the selection. Then in the early 90s up to the mid-90s, people started to propose the so-called Pareto-based methods. These algorithms incorporate the notion of Pareto optimality in the selection mechanism, but they don't use elitism. Some of them are very famous, like MOGA, proposed by Fonseca in 93, NSGA, proposed by Carl Jamoidev in the year 94, and is not so popular MPGA, the niche Pareto genetic algorithm. Then we have what I call the contemporary algorithms. These are elitist in the sense that they retain the non-dominant solutions generated at each iteration, and these non-dominant solutions are compared with the ones that are generated in the following iteration. Elitism is very important because theoretically it's required to guarantee convergence of a multi-objective evolutionary algorithm. So these algorithms, the most famous, of course, is NSGA2, is the most highly cited paper in engineering in the last 20 years or so. It was published originally in a conference in the year 2000 and in a journal in the year 2002 in the Transactions on Evolution and Computation. And there are, of course, many algorithms, most of which have been forgotten. And most recent algorithms, based on interesting ideas, we have like two new paradigms. MOIA-D, which is based on decomposition. This is also called escalarization, and it's a very interesting idea that comes from operations research. The idea is to transform a multi-objective optimization problem into several single-objective optimization problems that are solved simultaneously using neighborhood search. And this algorithm is very efficient. It requires, however, the use of weights. So as we increase the number of objectives, you need more weights, and therefore you need a larger population size. But the increase is linear. In Pareto-based selection, normally these algorithms don't scale properly. As we increase the number of objectives, they no longer work. And then we have indicator-based approaches. This is a very intriguing idea. Somebody discovered some years ago that it is possible to select solutions without using Pareto optimality. There are some performance indicators that are normally used to assess performance that can be used to select. There is only one that is known that has the mathematical properties that are required. It's called hypervolume. And the disadvantage of this indicator is that it's too expensive to compute it, particularly in high dimensionality with too many objectives. So today, algorithms used in this area have two components: a selection mechanism that may or may not be based on Pareto optimality. It may be used. It may use perhaps an indicator, and a density estimator, which is responsible for maintaining diversity. There are a number of density estimators that have been proposed over the years. In the old days, we used fitness sharing. Today, people have been using either performance indicators or clustering, or some people came out with the idea of using parallel coordinates, some methods from computer vision. There are many applications. I'm not going to get into the details, but there are applications basically in all areas of engineering and science. Some of them really nice. This one is for designing spaces, like an architect will do it, using a multi-objective evolutionary algorithm. This one, which is based on differential evolution, and another algorithm called uncolony, which this is not an evolutionary algorithm, it's also stochastic, but it's based on a different metaphor. This is used to design tour routes for tourists who want to go to some city and visit certain attractions. They try to optimize the tour. For radiation therapy, there are many in medicine that these are normally combinatorial problems related to some sort of scheduling problems that have been tackled with multi-objective evolutionary algorithms, because normally there are several objectives that you want to consider in the mathematical model. And this one is in software engineering. This is an application that was developed for a company that has these portfolios with software projects, and they want to decide how much money to invest in each of these software projects, so they use a multi-objective evolutionary algorithm to decide that. So if you want to know more about this topic, I do have this website. It's a repository in which we have a very large database of references. We also have public domain software in several programming languages, in C, C++, Java, Python, MATLAB. And also some contact information of researchers working in this field. So it has more than 12,000 references to give you an idea of how this field has been growing in the last few years. Just to give you an idea, when I got my PhD back in '96, I could not find more than 100 references on evolutionary multi-objective optimization. That's all from my side. Thanks a lot.
So now the time to get the chairs. Thank you. Yeah. So, Carla, Antonio. Humberto, por favor. Please. Please. Sí. Gracias. Sorry. So we will try to stick the time, of course. So this is going to start the discussion. We have here some questions just to start the discussion. I want to ask you, panelists, to stick in 2 or 3 minutes in these questions. The first question is maybe ambiguous because there's the word exponential. So the question is there an exponential symbiosis in the development of artificial intelligence or the application of artificial intelligence in science and engineering? So let's gonna quote exponential. So who wants to start? Here.
I don't think exponential for the moment. Although somebody thinks that artificial intelligence is exponential, I wouldn't add exponential to in this case, because and it depends also where. If you talk, for example, in reference to a well-developed country, we can more or less say this, but in a country like Mexico, it's very difficult to to say that there is an exponential symbiosis in artificial. I think we do very nice job, but we are doing our best for the moment.
Okay, well, I agree in the fact of exponential. I don't know about that, but there's definitely a symbiosis between artificial intelligence and science. In particular, well, in my field in genetics and biology, where we have seen like very promising methods, like more traditional deep learning type of approaches, is, for example, to characterize the non-functional parts of the genome. So definitely aggregating like many different type of data that we have here and learn more for biology has been, AI has played a very powerful tool. And well, in terms of like how, and I'm guessing that questions that arise from science can also be a motivation for developing more AI algorithms.
Yeah, well, it's definitely non-linear. I'm not sure if it's exponential, but I think the attention is exponential. And for me, the question is, how long is it going to last? Because this is cyclic, right? We had a boom when I was a PhD student in the 90s. There was also a boom on AI and parallel computing as well. US, Japan, they were putting a lot of money, Japan in robotics, US in parallel computing, but it didn't last that long. So for me, that's really the issue, if it's going to last. Right now, it's in the media, and many people are paying attention, but AI was already in our cell phones, has been there for a long time. It's already in many applications we have, in a lot of software, in many things we do in cars. So it has been there. It's just most people didn't realize on the things, this AI, that most people don't know what it is, what AI could actually do in terms of the impact in our everyday life. And I believe the issue is if, in our case in Mexico, as Humberto mentioned, that we don't have that much funding, if the government is willing to put the money where their mouth is, because they are now saying a lot about AI, as everybody else, and that's the question. Apparently there will be some money, but we will see.
So I agree the word exponential is kind of hard to internalize. Like I wouldn't know what exponential feels. But to me, it does seem like artificial intelligence has a radical effect on like engineering and science. For like a very, very palpable example would be X-ray crystallography. To determine the structure of proteins, it's so extremely complicated. People take years and years doing experiments trying to more or less figure it out, and out came DeepMind with their AlphaFold algorithm, which is reinforcement learning based something, and they participated in the annual protein competition, and they won first place by a ridiculous landslide. So imagine this opens the door to radically new avenues for exploration in science and research. So to me, that feels very exponential, I guess. Yeah. So yes, I'd say yes.
So yes, of course, we must think also on particular areas. Let's gonna just remember that genomics had a boom since 2000s, and the symbiosis between some let's say AI techniques, just to sketch the word, and genomics entirely, and let's say with these almost 20 years, we know this exponential growth and applications and the symbiosis in this area. But it's a very particular area. We can have also some other examples. But maybe what is interesting is that how can we construct an agile and diffusing, it means to the general public, an artificial intelligence-driven science and engineering ecosystems. Maybe we can put out the science and engineering ecosystem, but maybe genomics, transportation, and something else. Maybe Carlos, you can start this.
Sorry.
Okay, well, that's an interesting question. I think we know how. We don't have the resources, perhaps, to do it, but we have an idea. I think well, it depends on what the goals are, right? If you really want to build an ecosystem in which you can have multidisciplinary research getting a benefit from AI, then we will need to create some sort of institute, some sort of a structure that allows this to happen and that allows the communication in a very efficient way around the topic of AI without focusing on a specific application. It's more like for whatever you want. And you also need to do, of course, a lot of basic research to get to that point. But in Mexico, this, again, is complicated because normally there is a lot of, I will say, there is not much interest from most scientists to work together. Even in small disciplines, in small areas, within computer science at least, is very difficult. And in some institutions, they even encourage not to do that. Like my institution, for example, in Simbestab, you get like funding based on the research that your department does, and if you collaborate with another department from Simbestab, then you have to divide the money by the 2 departments or the 3 departments. So this doesn't encourage much to collaborate. If you collaborate outside, it's okay, but inside the same institution is not promoted by the institution itself. So, and in Mexico, this happens a lot, and we have scattered many researchers, some specialists in different areas, and that way is very difficult to interact. There have been some efforts in the past to do it, but it's difficult. But getting to the general public is a completely different issue, I think, because at this point, I believe we are seeing similar things that we saw in the 90s, that some people are afraid of AI. The question is not what AI can do for me. The question is it dangerous what AI is doing right now? And these questions we had back in the 90s as well. This is just coming back, you know.
Have the same
now
cycle.
even I am scared. So
Yeah,
because it's, at that time I was not scared because I was, as these kids, was young, but now I'm scared as well.
Yeah.
But the problem is, and this has to do a lot with ethics related to AI, which is another interesting topic, that the impact that it's going to have, and we had this event before this conference a few days ago with some people from France, and they were discussing some ethical issues in France related to privacy, for example, to the protection of your own information, to what extent will you allow computers to access this information and use it for your own good, but sacrificing your privacy. So there are many other issues on the other side. But the ecosystem in Mexico, at least, is a complicated idea. We all know how to do it, I think. It's just difficult in practice to do it.
Yeah. Antonio, maybe you can continue?
Well, I might give a naive answer, but like to create such an ecosystem, I think it's important to democratize knowledge, and probably open source would be just the way to go. Whatever research you do, you open source it, you make it available and easy for other people to use. And I mean, that way, let's say you're a researcher in biomedics, you know nothing about reinforcement learning, but then you can just quickly grab a tool from somebody else who does know it and just start putting these building blocks together. That would be mine.
Thank you. Carla?
So, first, to follow up with Carlos' comments, I would like to encourage all of us, especially starting for this room, to try to collaborate more. I mean, if it's pervasive, the environment of not collaboration, well, we should break it, and we should try to communicate more with each other and bring ideas together and yeah. So if we believe that we can actually change the environment, I think it is super important to come up with ideas, interdisciplinary ideas, and find a way to incorporate AI into different research and science fields. So, for example, what I've seen in where I'm working right now at Mount Sinai, there's like an open effort of incorporating AI tools into the clinical practice. And something that people there always say is like, you always need to have a physician in the room. You always need to have someone, a physician in the room when you're presenting them your models. Because then you probably, I mean, it's very easy as a theorist to come up with a problem and then go to your computer and just start working on it without knowing what actual information the physician would like to have. So trying to promote this type of collaborations is super important. And yeah, I think this is the future if we do want to have an active involvement of AI in the science and health.
Yes. Just to end up, I think the first thing, in my opinion, is to want. I want to do it. So the second is we need some politics and strategies. Okay, that's what I think we need. That we need money. What else would we need? That there is a respect for our work. I will give you an example. For example, now in our research system or evaluation in Area 7, if you have a work with more than 5 people, it is not taken into account. My question is why? So it's a way to just to kill multidisciplinary work, in my opinion. So we have to respect the work of everyone, because the work of everyone is very important. So we have to learn to work together. Each one has to do what he knows to do. For example, we have to educate, we have to produce new knowledge. The government has to do what he knows to do. Industry has to do what they know to do, and also society. In my opinion, there are several ingredients that are very necessary to do this. And in Mexico, in my opinion, because we're in Mexico, we are learning to do this. We have to learn a lot more.
Thank you, Humberto. Maybe, of course, could be a general question because artificial intelligence is on the spotlight right now. And if we take advantage of this spotlight, we can maybe enhance all of these conditions, or at least some of them. And for that, maybe, I don't know if it is possible here in Latin America or in Mexico to have that, for example, artificial intelligence research could become a driver for a more sustainable world or a better society nowadays. So what do you think? It's really an open question, just to give, of course, the time to the audience to ask around it. So, Antonio?
The answer is
yeah.
I mean,
obvious.
whether I think it could play a role, I say yes. But I would say, like, in order to create a better environment in general, research is important, and a very important or a very prominent tool within the research area is like artificial intelligence and optimization and all that. So I think they go hand in hand, and it's vital for us to leverage them in order to obtain nice results.
Yes, Carla?
I haven't come up with an answer. You put me on the spotlight.
Please, Carla.
I have no
You're on
idea
the
how to
spotlight.
reply to that answer. I'm trying to make up my mind.
Please.
Yeah?
Yeah.
So, could you repeat the question?
Yeah, can we have a better society?
Yeah, sure. We can.
Well, your insights,
Sorry?
your thoughts?
My thoughts for that. I don't know, like, what would we, I'm going to turn that back, the question to you, like, what would we need to have or do in order to use AI for trying to build a very more sustainable world? Like, I'm not sure about which tools and how can we push for that.
No one knows.
Okay, okay.
So, yeah.
Well, I guess a clear example of that, whomever were here yesterday, there was a panel for AI and social goods and all that. So naturally, I would say the answer is yes. Is it a driver? I mean, I think research is the driver, not mainly AI, but AI is a good tool within research. So.
Yeah, so as a tool, yes.
I think, again, the issue is not if we can do it, because there are several examples in which it has been shown that it's possible. The question is if we want to do it. Because, my main concern right now is we are living in a crazy world with presidents like Trump, Bolsonaro. So I'm not so sure they are interested in using AI as a driver for sustainability, because they are not interested in sustainability at all. So if you are not interested in that, AI becomes irrelevant in that domain.
So just to that, I guess then the question kind of delves into more about the type of people who does AI research and why and how they can use it for. So it's more about like ethics and about how as individuals we want to develop research rather than AI as an entity that, yeah, that acts like itself.
Okay. Yeah, I have it. Do you know what? One of the most important things when you apply technology is ethics. So, for example, in the careers we are opening in Polytechnico, several of the courses are related with ethics and using of this kind of technology, because artificial intelligence is not a very simple as a knife. Artificial intelligence has a much more profound impact in the world. You just push the button and that's it. So the question here is how to use it. For example, there are enterprises that 1 year they establish an ethics group, and the next year they disappeared because they don't get money. And always the question is, and I don't give just the names because I don't want to quemar, okay, as we say in Spanish, but there are enterprises like this that 1 year they open the ethics group and the next year they just disappear because of money. So the question is, how do you use this very important technology over center around the humanity? Okay, that's the question.
Yeah.
Well, I guess just to provide some controversy because it's nice. You guys talk about ethics, and we need to think about whether we want to use it or not. But for example, if you're developing a system and you know that by using AI tools, you're able to classify in a much better way. Like, there's absolutely no question that it is a very good tool to utilize and to exploit in order to enhance your research and get better results, regardless of the ethic question, right? So it is a driver for research and science. I would just food for thought.
Well, maybe we can continue the discussion. We have time. We have time for questions. Maybe we can start the discussion. Maybe over here. Yeah.
Hi, my name is Joaquin, and I have 2 questions. The first question is for Dr. Carlos. Returning to your comments about the 90s, do you think that a new winter with the artificial intelligence field could happen soon? And the other question is for Dr. Humberto. Do you know a group, an active group that is studying about ethics applied to artificial intelligence?
Yeah, regarding the winter, we didn't have a winter in the 90s. What we had was lack of interest. So that's what may happen again, because these things are cyclic, right? They are now a lot in the media, but that doesn't necessarily correlate with the amount of research that is being done in AI. Research on AI has been done for a long time. So it's just the interest. This interest goes up and down, and that's what I was referring to. But the interest is important in a way, because for us as scientists, we can get more funding if, AI is in everybody's minds, as opposed to having this as a hidden tool that most people don't know what it is, and some people are even afraid of. So for now, this boom in the media is very positive, at least from my perspective, in general, particularly in countries like Mexico. It's just we're probably not investing as much money as some other countries are investing, like in Europe and in China, in Canada. We have several examples in which some countries have put a lot of money on specific research centers, research groups that are doing research only on AI, on different branches of AI. And this is not happening in Mexico so far. I think we should get into this wagon. I hope we do. There are already proposals in that direction, but this is, of course, different from not doing research on AI. I think that's not going to happen. What may happen is people will get used to it, and they won't be talking about AI anymore because it's already there. You know, they see it every day, so nothing surprising about it.
Okay, so going to the second question, of course, in the whole world there are many groups working in this direction, but you know that ethics is not, it's very difficult to define because for country to country, the definition of ethics is different. For example, in China, the definition is completely different compared to maybe the States. So it depends. But what we are doing in that direction in Mexico, I know some groups, for example, in the academy, in the engineering academy, we are working in a manifesto, okay? Manifesto that establishes a position. That's one example, but there are much more examples. I am sure that Miguel, for example, or Enrique, know more groups working in this direction. But, for example, in our institute, we are also working. Once this research net is established, one of the documents that will be generated, it's a manifesto about the position of our institute concerning artificial intelligence and machine learning and related techniques.
Yeah, I want to make it's more like a comment on this, particularly on the question of the exponential growth. And I think that currently we have an exponential growth. So the applications of AI are growing exponentially. Maybe difficult to tell the exponent, but exponential. But I think every exponential growth cannot go forever. No? Even Moore's law, it seems, is coming to an end. And I think the same will happen, and I don't know in how many years, because also what we can do now with the current AI technology solve some types of problems, mainly prediction problems, classification problems. But there are more problems for intelligence that we cannot solve. So we will get to a point that this technology is not longer going into too many more applications, and then we need like a next jump of other technologies that will kind of another application. No? So that's my view.
Do you want to add a comment, maybe? No? We have a question here. Yeah, you.
Okay, Jorge Nocedal. There's a lot of talk about artificial intelligence, and it's confused with machine learning. Machine learning has a very low entry point because there's a lot of software tools out there. So I think this is something that you can just start doing. You don't need big organizations. The main investment is in hardware. You may need to have some CPUs. But I think, instead of waiting for government organizations or something like this, start doing it in your company, start doing it in a program within your university. And I say this because I was a faculty member here in IMAS, and in meetings, usually, 80% of the time was spent complaining about something. But it was not so easy to do. It's not so easy to become a nuclear scientist or so on. There's a real opportunity with machine learning in particular to just do it.
Hi, my name is Manfredo. So far, it has been established that AI, as a general term, is an excellent tool to solve problems. Can't we use AI to solve the ethics problem?
Someone? Humberto is.
No. Okay, well, I will be a very short answer. In my opinion, we are at the beginning we don't know yet which are the laws or the principles that govern intelligence. For example, we have the laws that govern mechanics and you know that. But in artificial intelligence, we don't have this set of equations. But we have shown that we can do several things. You can imagine what we will do when we discover this set of laws.
Well, I guess it all depends on how you define ethics, but yeah, come up with a cost function and just download TensorFlow, boom.
Good. Well, yeah, we have another question over there.
Well, I have a question for Antonio. Well, you are like a student at MIT, and you are working with space robots. Well, there are recent news about private enterprises or countries like China or India. They send like rovers to the moon, and also like Blue Origin and SpaceX. They're like giving like huge investment about space exploration, and specifically about space robotics, about like making a map of the moon or maybe Mars, or mining, or making a like well, what are your perspectives about the future of space robotics, given the recent news about these countries and these private companies? What they are doing, why they are investing like millions of dollars, and if there's a competition between these countries, between these private companies, and will they like mine the moon, or like recollect like natural resources? I don't know, or maybe like be like the first in technology in the world. I don't know. And also I have an open question about. I saw a tweet about the head of CONACYT that had a conference with some researchers, and I want to know like if there's a motivation with the new administration or about like giving opportunities of new advancements. For example, like the government, if they free the data about like the secretaries, like for example IMSS, it will be like very beneficial to the population, because if we could like prevent diseases like easier with more data. And well, that's it.
Tony?
So I guess for the second question, no clue. For the first question, why are they doing it? For private enterprises such as SpaceX or Blue Origin, I guess they're doing it, it's a business, right? They're doing it to make money. So they're mostly investing a lot in space tourism, so that's what they want to do. And space is actually a really powerful asset for anybody in any country. So everybody always wants to put satellites up and mine asteroids or whatever. So it's an economic investment that they are actually making. For countries, it's to establish some sort of like dominance or assertance amongst like the other countries. That would be 2 cents. But I mean, in general, any sort of investment within space exploration grants us the possibility to further broaden our horizons and start collecting more data about the universe, the origin of life, and all of that. So we as a society benefit from all of these endeavors, I guess.
Yeah.
About the second question, come tomorrow to the panel on the Center for AI.
Yeah, that's it.
Okay, and to the first, I agree with Antonio. That's the first, it's economics. But the second is, where do you think is the future for humanity? Where? Is here or is up there?
Here.
Okay, I agree with you. I agree with you, but what we are doing, humanity? So probably in very few thousand years, I don't know, maybe we will see the Earth, but completely destroyed. So that's also another motivation, because we have to think that Earth is our beginning home, but we have to think also in space. That's the second motivation, in my opinion.
Okay, any additional questions? Last one? No? No? So let's gonna close the panel. Thank you for your time. Thank you. So we have 15-minute break. Thank you.
Hey, hello everyone. So just please try to be on time. I know it's very little time to get coffee and come back, but we're having a very great speaker here next. And after that, we're going to have, again, the social event with posters, and please also stay for that.
Find some time. I know. But we will email you. We were in the meeting.
horrible things, and then how can we count something? Don't know. I don't think we can actually inhibit this. It's not better rehearsal sentence. Hello, to meet you. It's nice the weather. Is it possible to take off that, you get stuff? I think it works better to be on the positive side, to try to change social norms, regulations, laws. Gracias. Thank you very much.
The last one.
It's more productive to bring global understanding of the issues to the public and to the politicians. National and national regulations minimize computers. You're not going to be able to prevent development. Because it's,
what you cannot prevent, you should
organize.
¿Cómo estás? Corriendo, Gustavo. Vi por ahí ayer una foto tuya ahí. La foto de mi padre. Sí, pero fue porque fue y hasta el final algo de estrategia. ¿Quién lo armó? Los chavos. Me tocaron.
Thank you.
No sé si es
Good night. Good for me. I'm a cold person.
Y por ser el platillo y acabó con un no, hay que tener por el tweet porque ya lo puso ahí y alguien lo reyó. Y lo vi y dije, bueno, es que yo estuve aquí ayer en la mañana, entonces esto fue ayer en la tarde. En la tarde, sí, dije, mira, aquí varios de los que vi están allá. Sí, yo no sabía. Nada, no esperaba pero era una propuesta entonces al final tratamos que ese va a ser un punto pero no más no atomizar la cosa sino claro, no, muy falsas es que pero ¿cuál es lo que a ella no le gusta? Pues que sea como muy difícil. Pues, porque puedes decir, esto es para el pueblo. Y le dijimos fracasó porque estaba dentro de la sí, el consejo que tú haces. No, el consejo sí. Con ella estuvo ahí. Yo soy ahí. Y nos desmantelando. Ahora, eso es parte de la UNAM, eso es parte de la UNAM. Nos estamos a nivel para no quedar bajo. Entonces, este modelo que estamos planteando es algo ambiente, mucha libertad, estos centros de profesor, negocios con un objetivo pero esa parte de los
Do you read my book?
Porque en el foro ya saben, no se hagan bola. Entonces, pero al final, empezó a decir después de otras áreas, habían hecho la provincia de que era mejor. Sí, fue muy interesante porque saben que tienen los que son muy populares así para él. Y la reputación non-fiction muy utilizada, pero obviamente tampoco Bolívar lo que puso de Cuba si era bueno, porque al que te robo de repente no se tuviera como tú, oye, entonces ya, sí, ya lo después de 5 minutos para los chavos, ¿sí?
Hopefully not too much.
Pero de repente, bueno, se van y ellas, entonces se quedan solitos y ya les convencen. Y así andaba varios de los que dicen que le hacen. Yo no veo por dónde pero y entonces ¿cuál es tu impresión? ¿Tú crees que se vaya a pasar? Intentar hacer
you don't need to worry about it. But if you're always like worried by you cannot be efficient, then you need to work a lot of hours. You need a place where you concentrate.
Sorry. Eso me difícil con él, amigo. Siempre está atorado. Incluso yo pues ya la gente de Roma no se quedó en entonces a partir de eso se encabezaría ese incluso a Roma se le prestó es que esas restricciones entonces se habló ahí y está interesante el modelo que es básicamente un modelo se movió pero en donde tenían un nombramiento posiblemente como una licencia porque lo que quieren es que
es un personaje.
pero le lanzamos mucho es que no tener bien para resolver después pues esas eran las cosas paralelas. De hecho, este es mucho de hands-on, así que Machine Learning ahora haber hecho un problema de salud, de medicina, de de la industria y empiezas con los valores. A diferencia de, no sé, de pero aquí sí es muy, puede ser paralelo.
Y se le dijo que en verdad, por ejemplo, cuando se creó este sector de la verdad, se hacía por ejemplo como muy socialista. Es como si
Sorry, I can't.
Okay. Pero dicen que ellos lo que hicieron es que usaron dinero de las provincias, eligieron que se universidades más fuertes, esta universidad porque si no, ¿cuántos centros tienen? Entonces, ellos los que hacen entonces tienes que ser
Antes no, esto es de otra temporada, antes era al revés, lo que quería, era doctorados. O sea, si lo ven,
sí, yo lo que pienso es que
no se lo venden ahí, es para el pueblo.
Yo creo que si sale, saldría porque incluso no tiene entonces, yo sé que no me interesa. Son por porque dice que era un proyecto de la bolsa y en Canadá se está operando el año pasado y nunca soltaron los niños, pusieron todo y se echan de culpa pero fueron estos grandes y se podría hacer esto porque los
aquí por hasta toda la dificultad, todos los simplificados, el área de salud, el área de todo yo de hecho como me está interesando mucho el tema, pero yo digo, desde la física siempre estoy viendo a esta posibilidad de en serio. Por eso estoy aquí, pero es una comunidad nueva para mí. Todos están perdidos. Entonces, de hecho, yo quién soy, pero ven el entusiasmo. Está aquí preparada. Entonces vienes a la tarde, todos lo quieren, a la tarta, no hay nada, está todo vacío. Y aquí ve, parece que espera el lunes a las 12 del día. Cualquier cosa, tú le pones ya al final, casi no
Gracias.
All right. So thank you everyone for coming here in time. We're going in now. Very good time. So now I'm going to introduce our last speaker, Alan Aspuro. So he has been also one of the people who's been pivotal in this meeting. He was also in the first reunion where RIIAA was first mentioned and then created. So Alan Aspuro was born and raised here in Mexico City. He received his bachelor's degree in chemistry, also from here, from the National Autonomous University of Mexico, and was later awarded a PhD in physical chemistry from the University of Berkeley. Alan is professor of chemistry and computer science at the University of Toronto. He holds the Canadian Research Chair in Theoretical Chemistry, which means he was recognized as a top-tier researcher in his area by Canada 150 Research Chairs program. In his own words, his group works on the interface on theoretical chemistry with physics, computer science, and applied mathematics for the multiple applications, including molecular discovery. His group has worked on the robotization of chemical laboratories for large-scale experiments. This work has been mentioned among MIT's 10 breakthrough technologies. He's also an entrepreneur, so he has built several startups. And so please join me in giving him a very warm welcome.
Thank you. I want to follow up what Jorge said. The most important thing about this meeting is the enthusiasm of everybody. That is just the most amazing thing for me. So thank you for being excited about AI. So today, the story is that I was invited at my school at chemistry tomorrow to give a talk. So I had the luxury of splitting the topics I wanted to talk to you in two. Okay? So today, I will talk more about the deep learning related things, generative models and molecular representations. And tomorrow, in this talk, that I like the poster, I'm going to talk about more about Bayesian exploration of experimental parameters for chemistry. I'll show you videos of robots and things like that. Okay? So the other one is going to be more chemistry-oriented, and today is going to be more model-oriented. So to begin, I just want to give you a little bit of setting. Some of this I talked to you about last time before. Why AI for materials and molecules? If you Google the 21st century challenges, you will find out that materials and molecules are involved with many of them. You can read them here on my slide. But for example, think about water filtration. We might need cheaper water filtration membranes. That's just one example where everything that you are surrounded with could be optimized. And AI plays a big role in that. Say you're not a hippie like me, but also you want to make money. Turns out you can do that as well. Barron's, which is a journal that advises investors, actually says that, it talks about 3 technologies that could create $1 trillion markets over the next decade. Okay? Turns out I have 2 startups in two out of the 3, so that's pretty cool. One of them is quantum computing, which I work on. But the other one is very cool. It's AI for materials, and you can read here what they say about it, the combination of AI materials and AI robotics to accelerate the discovery of materials. And why is that? Because there is a big movement of AI for science. And we had a panel earlier on this kind of idea. This article by David Rothman in the MIT Technology Review is extremely to the point. If we reinvent the way we invent stuff with AI, we might be able to accelerate science in all sorts of fields. And that in turn actually provides a lot of benefits to humanity. So this is kind of like the more commercial idea, but both of them actually converge. So what is the challenge? Just very briefly.
Roughly, we can make about 10 to the 180 molecules. The estimates come from pharma. And it's basically the amount of chemical space that is reachable. In principle, it's infinite, but in practice, let's just imagine it's about that size. Okay? I'll tell you later, if you want, offline, how to come up with that estimate. And routinely, with machine learning projects, we treat millions of molecules. We can do perhaps hundreds of thousands of them doing more rigorous quantum chemical calculations. And the problem is sometimes the human brain. We created an application called Molecular Tinder for a project with Samsung, where you actually were looking at molecules and trying to figure out if they were synthesizable or not. And like in Tinder, after about 1,000, you don't care, you start swiping randomly, right? So a human has a very low attention span. And even worse, actually, there's some chemists in the audience. How many people are chemists? As the chemists in the audience know, it's very hard to make a molecule. It takes about 6 months sometimes to sit down in a hood and actually make a molecule. So in a typical project in my lab, you only end up making about 10 molecules that you theorized. So it's a huge funnel of possibilities. So I am interested in materials for these type of applications, and I'm going to give you an example of one, just to motivate you. Batteries. Humanity has not stored energy in large scale. We have stored tiny amounts of energy compared to the amount of energy that we need to store. If we want to go fully renewable, we need to store all the energy that we produce in the day at night. That will require an immense amount of material, and it has to be the cheapest, non-toxic, and most available material we can, because really this is going to be a transformational thing we need to do in the next century. So let me just see a person I really admire tell us about batteries.
And it's a company that provides multi-megawatt energy storage solutions using, and I have no idea what this is, vanadium redox fuel cells. That's one of the coolest things I've ever said out loud.
That's a president, okay? Just remember that. This can happen. So he's great, but he was talking about vanadium redox flow batteries. So I'm very interested in redox flow batteries, but there's not enough vanadium in the extractable piece of the core of the Earth to store the energy that he's talking about. So even smart presidents like Obama can tell you lies, like there's not enough vanadium, right? So about 5 years ago, at Harvard, when I was still there, we started screening with computing and doing intensive science cycles and came up with a molecule, in this case it's called anthraquinone disulfonate, that is similar to the molecules that you have on your body, and it's a potential candidate. It turns out it was very close to the desired molecule to store energy in these batteries. And this is not a chemistry talk. Tomorrow come to my chemistry talk to learn more about it. But the way these batteries work, they actually have 2 solutions of chemicals, and you can either charge them with a solar cell, or a windmill, and then one of them is going to have more electrons and one less, or if you want to roll it in the opposite direction, you can extract energy from it. Okay? So we already solved, after 5 years of research and $5 million, and that's important. Okay, this is the first paper. You get a Nature paper, you're very excited. This is our prototype flow battery. These are my collaborators. 5 years and $5 million later, we were able to actually come up with this molecule. We call it metuzalequinone. That molecule already absorbs one of the size of the battery because it fades 0.1% a day. So that basically means that you can have it decades. Okay, and then you refill your battery tank. And this is a derivative of oil, so you just make it as a fraction of a petrochemical and doesn't require metals and heavy extraction, right? So it's a very cool thing, but we still need the other side, but I don't want to spend another 5 years and $5 billion. So we started thinking about this, and Mexico plays a big role in this. We started thinking about how to break this funnel issue of 400,000 molecules or so calculated, but only 40 or so made. So what we proposed is this idea of materials acceleration platforms. These platforms heavily rely on AI and robotics to try to increase the throughput of materials discovery to a very modest goal, okay? Because what usually takes about 10 years or maybe 20 years and $10 to $100 million to take a material, say a new toner or a new solar cell material, from idea to market. We have 12 years to solve climate change. So I'm asking you for a factor of 10. I need AI and robotics, not even for a factor of 100, but even a factor of 10 will be amazing, and a factor of 100 will be transformational. Can you guys help me out, all of you, AI people, after all, I'm just a lowly chemist, to actually go down the pathway of molecular discovery and automate and increase the throughput of synthesis, fabrication, and testing. Of course, we have to get closer and closer to scaling of fabrication, but in some sense, reimagining our discovery processes and production processes to actually accelerate the finding of the materials that we need. So that's kind of like my cause. And Benjamin Sanchez, one of the organizers of the conference, please raise your hand. He is one of the rock stars in my group. He's now at Google. And Ben also gave 4 tutorials. He has 20 times more energy than I have. So Ben wrote this paper with me in Science, where he and I are writing about this laboratory. So think about it as a self-driving car, but instead of that, a laboratory that is making as many decisions as it can by itself. Right? You want to run it at night, it's making scientific decisions, you come in the morning, you guide it, right? But that is the idea. So therefore you have to have a big platform and pipeline of AI, software, and robotics to do chemistry, something that usually is not as automated as you want. Of course, pharma is the closest to that, but pharma doesn't really connect the pieces yet. Is this possible? Well, it is possible. The biologists, how many biologists in the audience? We heard a couple of bioinformatics talks. These people are the only people that have been able to do this. Beyond Moore's law, acceleration of the cost of genome sequencing happened in the next 15 years. So now sequencing a genome costs less than $1,000. Okay? If you were to go just Moore's law, when they started the Human Genome Project, will be about, I don't know, $800,000 or whatever for sequencing a human genome. This, of course, we heard earlier this afternoon about personalized medicine. This is the reason you can do this. So it is embarrassing for me chemists, for chemists or material scientists, not to be able to be as good as biologists, let alone the physicists. They're still thinking about graphene, and they only study 10 materials, the physicists, right? They think they're smarter than us, but I think the biologists are smarter than the physicists, then the chemists, and then the physicists, okay? So anyway, so we made and I'm joking, of course. So we made a workshop in Mexico that was very important, where people from about more than 20 countries got together and made recommendations about how to go about it. And of course, the recommendation is this closed loop platform I've been telling you about. We are developing a software called ChemOS to try to glue all these things together. So that's a big effort in my lab. I won't tell you too much about it, but this is what in pharma is called the make, design, test, and analyze cycle. Okay, so you want to be able to make decisions as soon as possible, and the testing is a big piece of it. So now, there's many elements of this materials acceleration platforms. You can read the report that we wrote back then. Today, I'm going to tell you, for the rest of this talk, of the topic of inverse design. So inverse design is the idea of given a molecular property or a materials property, finding out in that vast space, which is practically infinite, to the 180, what is the molecular material that solves your chemical problem. Okay? So that is the problem that we call in my field inverse design. So I think I presented this last time before, but this is a good introduction to AI. Okay, this is the movie Blade Runner. The best way to explain inverse design has to do with Blade Runner. This is 2019. That's why I love to talk about Blade Runner. This is this year, and this could be Los Angeles, right? With Trump and Kim, right? But the themes of this movie are AI and robotics. And how many people have watched it? Okay, so it's good. This is a very good representation. So for those of you that didn't watch it, I'm going to spoil it for you. So this is Deckard. He's a Blade Runner. He's trying to identify and kill androids. And here are some of his data points. And turns out that this is the solution. Okay, so these are androids and humans. And the big moral story is he himself an android or a human? But this is an important distinction, right? There are two tasks here. One in which you're trying to classify android or human. But body is the cool thing that we're going to talk about. These are models that actually generate human behavior. This is an android that is trying to behave like a human. So my group and others, but we were some of the pioneers to think about how to use these models in chemistry, right? How can I use these models, like are, in my sense, cooler, to actually do cool things in chemistry? So let me give you an example, right? This is artificially generated art by Google Art. And I will, if I sample you guys, many of you probably will get this wrong. This is art generated by androids or humans, right? So it was trained by a data set from humans, but then androids basically do a good job in painting abstract art, probably better than me, for sure. Okay? So let me show you one tool. Then I show you another tool, actually 4 tools, okay, and tell you how we have been evolving in our tool set building in chemistry. By the way, Benjamin is an author of this paper as well. So this tool is called the autoencoder. People have mentioned it in many of the talks. And of course, probably in the tutorials, this is a way of compressing information using a neural network and then decompressing it, right? This is an information theory way of thinking about it. For me, it's kind of like a channel where you're actually trying to find a compressed representation and then going back to the same sample And of course, you can use it to apply what we like to do nowadays, photo filters too. So you can decompress in a different way. So in this case, I decompressed this picture with this bald guy, like me, and made it like an art, right? So you have seen autoencoders are used for translation, they're used for all sorts of AI, and I'm not going to spend too much time in autoencoders, except for what I care about. What I care about in autoencoders is the fact that I went from a discrete molecular structure to a continuous representation and back to a molecular structure. So for the purposes of this talk, molecules are these graphs connected by atoms, right? And graphs are a very interesting data type right now in machine learning. And also sequences are a very important data type in machine learning. Turns out there is a mapping for any graph into its string. And in a particular case in chemistry, we call these strings smiles. Okay, this is going to be important because we're going to introduce an alternative. So Joshua's brother has this paper, okay, where they actually built a recursive neural network to build a text autoencoder, okay, at Google, right? So a technology that actually takes text, like the text you use for your cell phones, texting each other, and predicts, for example, what is the next character, or also creates a latent space of the text. Okay, so the interesting thing about these autoencoders is that they have to be generating this string probabilistically. And what is really cool about them, of course, is that you can interpolate in the latent space. As you see in these sentences from that paper, you can actually see sense from that interpolation. So my lab was extremely inspired by that technology, and we started thinking about, can we actually do the same for molecules? So let's go back and use that technology and take the molecular graphs and convert the molecular graphs to these strings that we call smiles, and then build an autoencoder for smiles technology. Okay, so that's what we did. Now, before I move on, one of the big areas in my field is, of course, molecular representation. We'll come back to it at the end of the talk. So this is a slide that Benjamin did, actually. You can see a molecule going to smiles, which is the sequence representation. You can actually use weighted graphs. You can use something called Coulomb matrix that comes from quantum mechanics. You can use a bag of bonds, which is very similar to bag of words. Or, of course, you can convert the molecule in this 3D atomic geometry and even look at molecular properties in that 3D cloud. So it's kind of like, now you can use methodology that people use for video processing, right? So there's a lot of wealth of AI methods that you can use, and the molecular representation topic is a very hot topic. Many people are working, especially now in this year, the fashion is to go this way, right? So that's an example of where people are thinking about a molecule for a computer can be seen in many different ways. And I argue depending on the application, it will have a different representation. So the genius of Rafa Gomez Bombarelli, and again, Ben is a co-author, and David Dubenot, Ryan Adams, and other people are in this paper, was the idea of taking this latent space and correlating it to a molecular property. So now we're going to actually, in a semi-supervised learning way, train a model that also shapes this latent space to correlate it to molecular properties of interest. And therefore, with an autoencoder, you can use any type of optimization, and maybe Jorge will tell us what is the best way to optimize in this rugged latent space. But we can optimize in the latent space, figure out what is the best molecule, project down into the latent space, and then use the decoder and ask the autoencoder which molecule is the molecule that has the maximum property for what I want. And that is inverse design, and if anything of this talk you remember is this idea of inverse design is important to chemists. So if you want to help us do inverse design, you will help the field, because you basically will help us make better solar cell, better drugs, etc. So what is really cool about this, in this particular case, these are stochastic methods because it's a variational autoencoder. So every time you enter with a molecule, you roughly will come out with a molecule probabilistically around it. So in this particular case, molecules that look like ibuprofen are coming out in a molecular distance metric. You can see how ibuprofen is quite similar to this graph and a little bit less similar to these graphs that have higher values for these distance metrics, called the Tanimoto distance. And the data lives in this kind of like Saturn ring of Tanimoto distance of about 16 or so around any molecule. So you have very few molecules that are so close to it, but of course there's kind of like a distribution of molecules that live around this particular distance, okay? Let's give you an idea of how we encode molecules. And what Benjamin did in this paper actually was to use Gaussian processes to fit to that latent space and optimize for a molecule that has a particular good property. And I'm going to come back to this during the end of this talk because I call it the Sanchez-Lenke-Link metric, because now all the papers in the field took our same data set, and this is the typical thing that happens in machine learning. We just came up with something, and now everybody's doing the same thing. They take the same data set and try to make the molecule more synthesizable and more drug-like. Okay, so that's going to be the metric that we just put in the paper, and now several papers are actually using as a metric, and we'll show you later how that metric compares. But it's nothing special about our metric. It's a data set of drug-like molecules, and this is a very simple to predict property. So it's nothing that is going to save the planet. It's just a numerical data set. It's kind of like NIST or something, right? Or CIFAR-10 data set. So this is the evolution of our thinking, okay? Chemists started doing direct simulation of the Schrödinger equation, one molecule at a time. In the beginning part of my career, probably from 2006 to 2012, I was just running a lot of calculations and then trying to see if I hit the jackpot. And then I learned machine learning from Ryan Adams and David Dubenot and others, and from Benjamin. And we started using these methods to do inverse design, and that accelerates us a lot. What is going to be the target molecule that you're going to be trying to design? So here is a menu of the different methods that people have used. So I'm going to tell you a little bit about GANs and also about evolutionary strategies, which is a new thing that is coming out of my lab. So GANs, again, this is work by Ben. This is actually his slide. You have a cop and a robber competing with each other to fake money. You probably have heard about this setup. It's like a game theory type setup, where you're trying to maximize the probability that the generator is generating realistically looking samples at the same time that the discriminator is actually trying to make sure they are fake or real. So in this idea, what we did is we added a reinforcement learning piece, right? We added a probability that every once in a while we ask this drug-like molecule generator to give us a drug-like molecule that has another property or set of properties, so that we bias the molecular distribution towards what we want. Remember, we need to do inverse design. We just don't like to generate random drug-like molecules. That's extremely boring for us. We want to bias the distribution towards what is useful for material science, chemistry, or drugs. I enjoy drugs a lot. So in this particular case, for example, this is a distribution before training. We're trying to make a molecule more soluble or more distributable between octanol and water. And then this is after Benjamin trained his model with reinforcement learning. He shifts the distribution to a very high value of this particular property, actually log P and synthesizability. So you see how this GAN was trained not only to give you molecules, but also to give you molecules that are useful, right? And since then, several things have happened. There is a startup company called In Silico AI that I collaborated with. In 40 or so days, they designed a drug candidate for muscular dystrophy in 46 days. Okay? I don't have the slides yet. I was doing slides for another thing this morning, but this Monday, the paper appears in Nature Biotechnology. So the cool thing is that this is based on Benjamin's paper of 2 years ago. There's a startup company using that technology, and actually was able to do that. And I'm a co-author just because I helped them a little bit in thinking about the paper and a little bit on the chemistry. They did all the work. So now I want to tell you something new. This is the work of a quantum physicist that came to my lab, and he has been thinking about the representation of quantum physics experiments. So okay, this guy does quantum computing, comes to my lab and says, I want to do machine learning. So I tell him, why don't you think about molecular representation and try to think about graphs or something, right? So this guy, Mario Kren, he's a genius. He comes back and says, okay, Alan, I invented a new method that is better than smiles. So now let's deep dive into the smiles. I show them to you. How do they look like? Okay, you can see these parentheses. Okay, they represent subgroups that are attached from one molecule to the other. These double links represent double bonds. And you can see colorized there, more or less, which parts of the string represent to which parts of the graph. So you can see that the graph branches out and then branches in, branches out, branches in, and it's a mess. The problem with the smiles is that most of the smiles that you write will be invalid. It's like if you are texting drunk, like Kopfefe, like drunk, like Trump. Kopfefe, right? What does that mean, right? So most of the smiles are actually syntactically wrong. For example, you might be missing a parenthesis, so you might be having a number that makes no sense. Those numbers represent rings. So you might be closing a ring that doesn't exist. Or all sorts of basically syntactical constraint errors, or even semantical constraints. For example, there's only 3 chemists in the audience, but many more people might remember that oxygen doesn't make 4 bonds. So this molecule sucks because it has 4 bonds of oxygen, but in some sense it's syntactically valid, but semantically makes no sense. It's like a baby combining words in another language. It doesn't make sense. So what Mario did, and then what people have been doing is, okay, they didn't really think about smiles, but they were thinking about ways of creating better models that actually incorporate such constraints in the autoencoder or in the generative model. In other words, they added a lot of processing to the encoding and decoding of the autoencoder to try to fix the grammar problems. Okay, so Rafael Hernandez Lobato in Cambridge, Tommy Giacola and Regina Barcila in MIT, and a bunch of very smart people in AI spent a lot of time trying to encode and decode better the information. Okay, but this is where we were inspired also by a paper of Noel Boyle that used reverse Polish notation. Do you guys remember reverse Polish notation? To deal with the parenthesis issue. So he created a slightly better smiles that, because it's written in reverse Polish notation, it has less parenthesis errors. Okay, but it was really not that super important change. And this is where it comes, selfies. Okay, selfies is our new representation. It's on the archive, and we submitted it to NeurIPS, so cross your fingers. We better hear soon. But what we really like about selfies is that selfies actually is based on what is called a formal grammar, a Chomsky type 3 grammar, it turns out to be. Okay, I don't know enough about those formal grammars, so don't quiz me on it. But let me explain it to you as a poor chemist. Think about a molecular graph as a subway map. Okay? Every time you enter a carbon atom, you know how many other carbon atoms you can bond to. Okay? You know that you can bond to oxygen or to nitrogen, but maybe not to this type of atom, etc. Okay? All of those rules turn out to be a finite set of rules that define the subway connection to all the possible atoms that you're going to be able to go to. Okay? So now, every time you have a character in the string, turns out the character in the string will, in some sense, define what are the possible characters that will follow it. Okay? So it's like a subway map, literally, that you follow, and you can only stay within the constraints of the grammar. So every selfie, in principle, and turns out this is what we had to prove to our NeurIPS reviewer, maybe you're here, we had to prove that, in principle, it can be 100% efficient, and now we show it. We have a computational case that we haven't found, so we're at 99.9% efficiency. So there's some strange molecules that we cannot really do still in the computer, but now we prove that it's 100%. Okay? So you can generate with 100% success a molecular graph. Okay? So that's amazing. And turns out that for molecules, this is the rule set. So that's it. Of course, we're missing stereochemistry for those that you know it, and we're missing hypermolecular bonding and a few cases. I mean, a little bit more chemistry has to be added as rules, but we are going to make a standardization group, and literally, this is the whole selfies for molecular graphs, right? For basically organic-like molecules. So Mario really, I think, made a discovery. And the thing is that these are branching functions that recursively you can enter, right? So there are some branching and also ring functions, okay? So you have rings and 3 types of branches, opening branches and closing branches. Sorry, opening rings, closing rings, and then different types of molecular branches. That's it. Okay? So, for example, to make this kind of, you can tell Mario is a physicist because this molecule is actually quite not interesting to a chemist, but he's showing the example of how he transverses this tree, and he creates a selfie that actually looks like that. That's the rules of the rule set of the selfie that represent that valid molecule. So, why are we so excited about selfies? Because now we can have extremely compact machine learning models that, for example, if I just randomize a selfie string, in our old results, we were about 80% efficient, 60% efficient, depending on the length of the string and details, compared to the validity for these very short strings of about 18% for a smiles, or 9% for the grammar BAE of Hernandez Lobato. Okay? But notice how the reverse Polish notation does help, but not as much. So this is how we were when we submitted the paper to the conference, but now again we got to 100% or 99.9%. So that then shows you that when you actually now train an autoencoder, for example, and that's why I was trying to tell you about the autoencoders with a selfie, you get, for example, I already told you about the validity. The autoencoder doesn't waste time and basically gives you only valid molecules, but also, as I show you in a couple plots, makes very diverse molecules. Okay, and
And these are just validity versus diversity and reconstruction probability versus diversity. So in both plots, the better in the upper right-hand corner, the better. So this gives you an idea of how smiles, deep smiles, and grammar BAE, which is basically a variational autoencoder fixed for the grammar, work for the case of generating molecules. Okay? So how about regression tasks? Well, we are as good at regression as the other models. Deep smiles, smiles, and us, for this particular very simple task of partition coefficient between octanol and water, we do as well, because you might think, well, if the representation is more compact, if it's a different representation of the graph, will you lose something or you will gain something? Turns out that for regression tasks, we're about the same. Okay? Now, to answer another one of our referees, they were asking us, well, I mean, if you have this representation, how dense is your latent space? Actually, Ben was the first person in my group that started thinking about how many molecules live in the latent space in the volume of it. Like as you're moving in the latent space, how many different molecules are there? Notice this is a logarithmic plot, so we are at least 2 orders of magnitude more diverse. So our autoencoder in the latent space has much more chemical diversity. So that's good, because if you want to use it to optimize chemical functionality, you don't want your molecules to be boring and look like the same, but you want your molecules to be exciting. So this tells you that our molecules are about 100 times more exciting than the previous efforts. So also, our reviewers were asking us, you know, this is a typical problem of reviewers. You remember a car before review and a car after review? So they said, can you do another generative model? So, okay, let's write a GAN. Okay, no problem. We have Benjamin's code, so we wrote a GAN, and we also show you that the GAN performance is better. We get more diverse molecules, better performance in the GAN. So autoencoders are also better. Selfies are better than the smiles in GANs. Okay? So then again, can we make selfies 100% valid? So NeurIPS only allows you to respond to the reviewer in a single page. So we put like 10 responses, and this is our condensed response of how we can make the molecules valid. Basically, we need to keep track of when the rings were opened and then figure out how the rings close. That's a very simple explanation. And basically now, again, the latest result as of the Slack of my group is that they are just trying to debug another case that they don't understand why the smiles is not 100%, but 99.9%. Basically, you generate a random string, and the random string will be a valid molecule. Think about that. That means that you're not wasting any machine learning resources on the grammar of the molecule. So people in chemistry worry about readability. This is a molecule, and this is how its smiles looks like. And this is how its smarts looks like. Sorry, selfie. Smiles and selfie. To me, they look equally unreadable. Okay, so chemists sometimes think that the smiles are readable. I think for a very complex molecule, they are unreadable. What you can see here is that you can actually just install selfies. It's in paper ready, so you can install the package, transform molecules from smiles to selfies and vice versa. And in a single week that we released the paper, there were already people posting in their blogs how they're using selfies, because basically you can download it and start using it right away for cheminformatics. So now, I'm going to say one thing. How many people here are undergraduates, licenciatura students? Okay, so for the end of my talk, I want to tell you the work of one of my undergraduates, Akshat Nigam, okay, which is my rock star in the lab now. It's like Benjamin 2.0, okay? Akshat is just, right? How do you think about that, Gabe? Akshat is this kid that is always smiling. I've never seen Akshat not smiling, okay? And he works with Mario, and he works with these guys. And Akshat came one time to me and said, we have a genetic algorithm that is working amazingly, right? Remember I told you there's another generative model that is very popular in the 80s and 90s. Evolutionary strategies had a huge comeback with this paper. I think it's cited more than 400 times because people started thinking that maybe they can evolve the parameters of neural networks and compete with other optimization methods because this is more parallelizable. Bottom line, we were inspired by that. And also Jan Jensen, this is the guy that in 1 week took our selfies and generated a generative model using them, and also smiles. But this is the problem of these evolutionary algorithms. They evolve, they generate a species, and that species then becomes lazy. It's like a typical problem in many of these algorithms, but in this particular case what happens is that you generate a molecule, and that molecule is fit enough that the algorithm says, I'm done. So he says in his paper, well, just restart it, and then see if it ends in another molecule. But remember, again, raise your hand if you're an undergraduate. You should be able to do this, okay? So he says, I'm going to read genetic algorithms literature from the 80s. This is what Akshat did on the weekend because he doesn't have any extra time. And he started coding these mutations in selfies. For example, if you take a selfie and you basically replace a carbon by a ring, then you can take this particular molecule on the right and make it this molecule on the left to the right. Or if you actually, for example, insert a branch or etc., you can change the molecule in the left to the right. So these are the type of mutations that he actually coded. So that's a selfie and the kind of things that we insert and remove. And this is basically Benjamin's code for GANs, but now the generator is just a genetic algorithm instead of a neural network. And what is cool about that is that he just took his basic few lines of Python that do these mutations, use selfies representation instead of smiles, and there we go. In a weekend, Action had this. But on top of that, he took the Sanchez-Lengaling penalty function, as I called it, the one that everybody's using. But he added a new term. Obviously, every time you add a new term to things and your loss function becomes better, things happen. And in this particular case, he found in the literature of the 80s this discriminator that says, as your molecule starts looking like the same, start penalizing that if it looks like the same. So in other words, the molecule becomes very fit, but then these numbers starts becoming smaller and smaller. This is the new value. And therefore, the molecule is being increased in the population rank of the genetic algorithm. It's making it less and less fit compared to the other molecules. In other words, it starts penalizing such a molecule, right? And the probability of killing it from our top list of molecules is going to be larger and larger. So just adding that particular term makes the algorithm do what we should perhaps do in this planet. Like, we generated the humans that are destroying everything. We should destroy them and generate another species, and then destroy the species and generate another species. But now this is automatic, right? You just run the algorithm, it generates a species and kills it, and generates another species and kills it, which is really cool because this is what you want, right? So that's what Akshat did as an undergrad. So this is the typical scan of that beta parameter, right? That makes it either what we were used to do before in GANs, which is be much more like the distribution of drug-like molecules, or completely bias it to the distribution of target molecules. Okay, so I'm not going to go through the entire slide for interest of time, but the point is that you can see how we increase this beta and the distribution changes a lot. One of them looks like the old boring distributions that everybody used, and this is our original paper. This is Hernandez Lobato, this is the MIT people, okay, etc. And this is the value in the Sanchez-Lengaling objective function. But now by jacking up that beta value, we can actually start generating very molecules that are tailored towards the distribution. So it's like biasing the distribution towards the molecules that you want in inverse design to the extreme. Okay, so now I challenge all of you guys, undergrads, beat Akshat. So I want to see a bigger value than this, okay? And only undergrads can compete. Graduate students are too old, right? So I'm super fan of Akshat, and this is basically the results that we generated maybe 2 weeks ago. It was presented in group meeting, and now I'm sharing with you. We're writing the paper. So how much time do I have left? This is the natural break point. Still have enough? Okay, so I'm going to show a little bit of the preview of the next talk, but this is just an animation that I guess it might animate. This is the two-dimensional principal component analysis projection of Akshat's molecules, and then we cluster them. And basically, he's just trying to animate how, as the genetic algorithm progresses, we're generating different types of molecules that are generated, and then after a while, they are killed because they become less cool. And here, you saw that we generated purple for a while, purple was king, and then we generated, you know, light purple, and then we generated green and another type of molecule. These are the different clusters of types of molecules as they evolve in time. And undergrads always like to make cool animations, and I decided to show you his animation because I actually like it, right? So it gives you an idea of what the genetic algorithm is doing. So what I like about going through this talk is that inverse design has at least 4 tools and maybe more AI tools, but I showed you, to remind you, I showed you GANs, I showed you autoencoders, and I showed you genetic algorithms to actually design molecules. So you can see that my lab is just taking the tools that machine learning has been using for a long time and trying to adapt them to molecular design. So, okay, so how much time do I have left? 10 minutes. Okay, so I'm going to go and tell you a little bit about robots in 10 minutes. Just give me 1 second. I went too fast. Well, okay. So tomorrow I'll tell you more about this, but I'll be shifting through my slides, perhaps just clicking through them. I apologize for that. But let's go back to the beginning, and let me tell you why biology is so way ahead of us. Turns out that to do a lot of damage in biology, you only need to make very few molecules. You need to make peptides. And how many amino acids make a protein? Do you got people know that here? 21, right? So if you make a robot that makes a very simple coupling reaction, and you use 21 amino acids, you can make all peptides. So in other words, you can make a machine that makes proteins. And that's extremely important because now people can just synthesize proteins in the lab. And this is a paper from 10 years before I was born, 1966, that already started doing that. And look at these cool diagrams that look so retro, right? So that's why my slides are with that background, okay? Then you want to think about when do people start thinking about AI for optimizing chemical processes, right? So now we're talking about a slightly different topic. We're talking about controlling the chemical process like a self-driving lab. So you might think that we are very creative, but turns out people in the 70s, I was already 2 years old, when people at SmithKline, which is now part of GSK, a pharma company, had a robot that actually went ahead and started doing chemistry in closed loop. Okay, which basically means that you control the parameters of the chemical reaction on the fly to maximize the production. Okay? So I want to ask people, how many people know what is design of experiments? Because I'm going to be comparing to design of experiments. Raise your hand. Most of you must be engineers or something like that. It's a very famous tool for actually trying to build a grid in multidimensional space to try to find out what is the direction where you should actually be finding improvements or correlations in your optimization. If you're a chemical engineer and you try to optimize a process, you probably will be exposed to something like design of experiments. And the question that my lab is thinking about is like, I don't want to use my robots using design of experiments, and I use my robots with more modern machine learning tools to explore chemical phase faster. So I'm going to just show you what a Bayesian model, in this particular case, Bayesian neural network, compares to Gaussian processes in a couple videos, and then I'm going to end the time for talks. So let me show you just one robot, the ones that we're building, okay? You see, I thought I was gonna speak slower, but I guess I drank too much caffeine. You want a robot with music or without music? Okay, let me show you a robot without music, but I have worst speed up in this one, okay? So don't criticize me for the speed up. This robot has very few variables, but it has music, okay? So turns out in energy, every technology in energy uses thin films. And making thin films is an art. If you have a human trying to make a thin film, what they do is something called spin coating. How many of you know what is spin coating? Let me explain to you what it is. It's a little machine that rotates. Actually, Ben has made some spin coating experiments, and probably you gave too. You drop some molecule or some material, and then you spin it at a certain speed and at a certain parameters, and then you drop the other one, then drop the other one, and as it is drying and spilling out to the sides, actually, it's very messy, it creates a thin film of your chemicals. And there are labs that have a postdoc that has been there for 6 years because they're a very good spin coater. So I want to replace those people with a machine. Just kidding. I want to make them much, 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 much more powerful, right? So founded by Canada, under the context of clean energy, because all clean energy technologies require thin films, we went to Vancouver and we prototyped this Canadian robot arm. This is an N9 robot. This is, of course, the people that did the experimental work are the heroes, Jason Hine and Curtis Berlinger at the UBC, and designed this robot that actually carries out the spin coating procedure. And you can see here the different things, the different liquids. This is a slide, and you're going to see here from the slide how you're going to pick up the chemicals, drop it in the slide, cap the slide with a PVC cover, okay, and then spin it. And then after that, there is a testing station, you see here, that tests electrical conductivity, and a camera that tests if the film is broken. And of course, we use AI for all these different pieces. For example, for the camera, we try to use computer vision, and of course, we use simple AI for correlating the structure property on the spin coater and so on. So a lot of these materials AI uses a bunch of simple modules, and the whole idea is to put them all together. And therefore, this is a robot. This is a made in Canada robot. I'm very proud. It's called AIDA, and it's the first thin film self-driving laboratory of the world. And we decided in Twitter that every time you show a robot, you have to put it with music. That's the rule, okay? So if you guys show a robot in this conference, you have to put music. So there it is. That's the robot uncapping, capping, taking chemicals, mixing the precursors, and actually doing chemistry hundreds of times faster than if you were a poor organic chemist, right? So with that, I'm going to end my talk, just showing you how the robot does its job, okay? Okay, guys, I'm going to actually go to the end. Turns out that this thing is only, because it's only two-dimensional optimization, it's only 3 times faster than design of experiments. But we are increasing the dimensionality of parameter space, and that, of course, will increase the performance of the model. So I'm going to end with a picture of my research group and hopefully have some time for questions. So thank you for your attention, and hopefully, if you're interested in this, you come to Toronto to study with me, the undergrads, okay?
All right, we have quite a bit of time for questions. Just please keep it brief and just one question per person so that as many people as we can ask questions.
And tomorrow, if you go to Facultad de Química at 11, I'll be talking about what is the AI piece that we use for the chemistry and much more about how many robot experiments we've done around the world. So if you're interested in that active learning type of scenario and Bayesian exploration and so on, come and see that other talk. Yeah.
Hi, over here. Over here. Thank you very much. That was a really interesting talk. I was curious, when you're using the autoencoder for generating new chemical molecules, you said you were evaluating an objective function in the latent space. And I was wondering how you do that, because there the molecules are represented in some potentially pseudo-random way that you're not necessarily able to measure the typical properties of chemical.
Very good point. So this is how we do it. So yes, once you compress, especially when it's as miles, once you compress as miles into the latent space, most of what the latent space organization looks like is an organization based on how close are two smiles to each other, which might not be related to the property you want to optimize. So what my team did, and this is the genius of Ben, Rafa, and others, was to semi-supervised train it. So they say, I'm going to encode the molecular graph and 3 properties, and decode the graph and those 3 properties. So now the distance in the latent space is molecule and property pairs. Turns out that when you encode it that way, then turns out that the molecules are organized more chemically, and then you can fit models to that latent space, and then even for properties that are not the properties you train with, you will do better than just randomly training it just in this shape of the molecule. Okay, so that's the answer. So we kind of bake in a little bit of the properties, and I think this is actually, I'm going to repeat Jorge's statement. You caught us with a detail, right? I mean, it's something that you need to add to the model that I skipped to make it work. Yeah. So we spent a lot of time trying to make it work without that. So that's a secret ingredient, yeah, that is in the paper, obviously, but it's something I didn't have time to explain. Okay.
Hey, Alan.
Yeah.
Question. I think, as you yourself mentioned, this inverse design and all the elements that go into it are some of the most exciting applications that I've seen because of the whole pipeline, making up a grammar, optimization, a generator, a discriminator, etc. So what else other than your domain, your application in synthesizing or designing molecules, have you seen application of this type of paradigm?
Oh, this is a very good thing. So turns out Canada, as Joshua will tell you, is the magnet of so many new AI centers and things. So it turns out in the same building that the Vector Institute is, there's an Autodesk AI center, which I went to visit because I was interested personally. I have an architect friend that I go drinking a lot. And I started thinking about generative design of buildings. Can I generate apartment complexes? With him, we started thinking about generating molecules. Why can't we just generate plans for buildings? So Eric and I found that actually AutoCAD was doing that in Toronto and New York. So we went to Toronto, and turns out that they used a generative model to design the office. Okay, so actually the office, it was actually a genetic algorithm. Okay, but they designed the office with a genetic algorithm that maximized and minimized certain properties, like how much light does every person get, how big is the office of the boss, I don't know, what is the coffee. So I was working for an office that was the instantiation of a generative design model. But even more exciting, Autodesk, is moving into the generative design for all sorts of applications like chairs, industrial design. They were showing in the office the design of some beams on a plane to try to lower the weight of the plane. So you can use it for designing parts, for example. So generative design, that's an inverse design problem. I want a part that weighs little and has this particular property and so on. So that's another example that is not chemical. But I mean, there must be others, but it's also stuff, but maybe people have other examples of inverse design. Any other questions? Yes.
Yeah, somewhat related to the first question. To what extent can these methods, these model-based optimization methods, can fall victim to like adversarial examples? So finding things that are close, nearby gradient-based, but not really useful in real life.
Yeah.
How can you mitigate it?
I really want to write that paper. That's the cool thing of being a chemist, that I see what's happening in the archive, and then I come up with ideas of what to do in chemistry. I want to find what does an adversarial drug look like. Sounds cool, like the paper, adversarial drug-like compounds. So we haven't done that, but maybe Gabe sitting next to you writes that paper. Yeah. Yes. Or actually Marta, which is sitting next to him, actually. Yeah. Marta, you should do it faster. Yeah. Yeah. Okay.
Hi everyone. Do you think there's a way to simulate human physiology to test the molecules that you are creating instead of test them in animals and humans and wait 10 years to be cleared?
Yeah, I mean, the people that are, I mean, this is a big discussion. You are touching on a very important topic. AI in pharma, if you just go to the assays that we're doing, might be not as inefficient as the old computer-aided drug design and the other pipelines. So there's people that argue that you really need to simulate what is the uptake in a living human or a living organism, as you are talking about. I don't know how to do it. I'm not a biologist. Maybe you are a biologist. You should do it. You're younger than me and you're a biologist. But yes, if drug design really it has a hope, has to go way beyond this lead candidate identification and then going down all these different assays to better understanding of the physiology. I believe that there's going to be a convergence because we're going to have more and more personalized medicine data. We're going to have more genomics and so on. And maybe we can have the genomics of each one of the cell lines that we're trying the things and understand more the omics together with the small molecule design. But I am not a drug designer, so maybe I'm telling you something very basic. But yeah, AI for drug design is a big topic, and there's proponents within pharma, there's opponents, there's academics that are in favor, and that one is very correlated with age. The older you are, the more skeptical you are of AI. Because there were broken promises before when people were doing simpler methods, like, gradient boosted trees and things like that. And ultimately, like if your representation doesn't change, maybe a neural network is about the same as those old methods. So they are justified to be skeptical. That's why I do materials, because in the material, my assay is a laser or something like that. I don't need to wait for 10 years for you to test a drug. Yeah.
Of course. Thank you.
Maybe we should do psychotropics. That's easier to test. Yeah. Yes.
So again, like in this computing framework or whatever, where you have, I don't know, in the case of light, a physical computing device with chemistry reactions, having some kind of computation work, building computers based on the computations that chemical reactions do, like simulating neural networks, for example.
So funny. I have 3 people in my group working on a DARPA project called molecular computing.
Okay.
So we actually are building a model. We're going to put it in the archive extremely soon. Actually, we just submitted the patent first, right? But what it is basically drops of ink that compete with each other and realize an icing model in paper. Okay. So you print a computational problem in paper and then wait until it dries. And when it dries, it's solved a discrete optimization problem. So yeah, so we're working on that, yes. Sorry, my lab is big and there's a bunch of crazy people. The people that are doing that at CU, what is CU, guys? Where is she? Next to you, Gabe? Okay, so CU, she's doing that. Yeah. And Riley, where is Riley? Well, anyway, there's 2 or 3 people working on that. Pascal, yeah. Okay.
So I remember you said you were working on quantum computing also. Well, with quantum computing.
Yes.
Oh,
that's what I started with. I am a newbie to AI. I'm much more older in quantum computing.
Well,
Yeah.
I work with that as well, but on a different application. So I would like to know what are you doing with that? Because
Let's talk about it later because it's not this topic of this conference.
All right.
Yeah.
Understand, thanks.
Yeah, just catch me outside because that's for the coffee break. It's like boring for this audience, quantum computing, in terms of it would take a long time to answer that question. Yeah.
Hi. How much chemistry and material science should a machine learning practitioner know to do material discovery?
It's a super good question, man. You notice that Mario is a physicist, a quantum physicist, and he built a new molecular representation. My colleague Rich Semmel, that works on graphs, really liked the selfies, for example, right? So I told him, look, this was not even done by a machine learning guy. So from the other side, it's pretty fast, and from your side probably too. It's funny because I haven't been able to hire many computer science postdocs. They all got to Google for extremely large salaries. And I was just asking Joshua Benyo, can you send me one? And he's saying it's very difficult. So it's very hard to get computer science postdocs. If you're a computer scientist trying to enter my field, please, by all means, send me an email because there's not many that want to. But I think you will learn enough chemistry to get by. And the whole important thing of multidisciplinary teams is that, of course, you hang out with Marta all the time, and she will teach you about batteries, and you will teach her about machine learning, and then both of you will become as hybrid, like a GAN, right? Like the generator and discriminator. You will be like the computer scientist and the chemist. So I think that's the future of science. So I think you should embrace, if you like this field, just should enter it, and you can learn it. But I don't have a quantification of that. You know, it depends on how smart you are. So if you're smart enough, you will be able to learn it, right? And I think you're smart enough, so yeah.
All right, let's thank Alan once again. And so, before everybody leaves, we have some super exciting announcement to make. So people from Kipu are going to come here now, and they're going to talk to us about super exciting news.
Hi, my name is Meire Fortunato, and I'm one of the co-organizers of Kipu. That's also an event that's aiming to strengthen the Latin American community in AI. This year we are going to host it in Uruguay, and we are very excited to be here and see the great community. I'm actually quite new to participating in events in Latin America in AI. This is my first one, and I have to say this has been one of the best conferences I've attended, and I always go to the big ones, NeurIP, Cyclear, but this has been amazing, talking to all the candidates, seeing the quality of the talk. It has been truly inspirational, and this just inspires me to keep doing the work and motivating this community. Thank you.
So I subscribe to the words that Meire said. Now Tonio said that we have a huge announcement. I feel a bit of pressure. So we don't have an announcement. We just wanted to say that, yeah, to tell you this. So this year we have a few applications from Mexico. We would love to have many more. And hopefully, so this idea of Kipu and to have a very close, we want to have a very, very close relationship with RIIAA. That's why we are here, and we are sponsoring this prize. So bringing two of you down to Uruguay. One of the goals of Kipu is to keep moving it around, and hopefully we'll host it here one day, not too far in the future. And so we thank to our sponsors. We were lucky to be able to provide many scholarships, and so we want to do that in the future as well. So please, next year around April or so, start checking kipu.ai, and hopefully you will be able to apply. And for those of you who don't know what Kipu means, so Kipu is this device. I want to say a computer that or let's say an information storage device that the cultures from the Andes used to have. And in order to honor our heritage, so we chose it as our symbol, and we believe that, so those were the early days, right? We believe that Latin America will play a huge role in the future of AI, and as Maria said, it's very inspiring to see all of you and the great work you're doing. We are very excited to go to the poster session. So anyway,
next year, be aware of, be clicking on kipu.ai, and thanks again for hosting us. It's been a true pleasure.
And that is the amazing announcement, right? That 2 full covered trips to this amazing summer school where some of the professors include Joshua Benjo, Jeff Dean, and very amazing people in the world. 2 people, the winners of the poster sessions, as you know, and there are many posters that we're now going to be showing in the session, are completely sponsored by them, and that's for that we're very thankful. And this is the website for Kipu, by the way. Thank you.
Thank you, Andre.
All right, so please everyone, so there's going to be in the back, so there's a poster session, there's drinks, there's food. And for the people that have the poster, again, please stay next to your poster. There's going to come people that are going to come and evaluate the posters. And again, as they mentioned, the best 2 posters are going to win a fully paid trip to Kipu.
Sí, quítalo, sí.
Okay. I don't know if it's really
Well, when you show the reaction, a lot of times with you, if you make this as a student, making those points is very hard. So you use something that facilitates this. Like there's an optimization process experimentally that's very awesome and very demanding. We want to avoid that by computational providing.